All right, hello again. Welcome to section 2.7, which is going to be about parent functions and transformations. So basically we're going to be talking about relations and functions that we should know something about, and we're going to be talking about how we can figure out how to graph them and transform them based on the equation. So today our goals are to identify parent functions and then to be able to describe and graph transformations of functions. So we're going to be able to do both of those things. So we have a lot of new vocabulary in this section that you should be looking for as we talk about it. We are going to talk about families of graphs, parent functions, and then we have specific kind of functions we're going to talk about. The constant function, the identity function, the quadratic function. We will talk a little bit about absolute value functions, which we talked about in our last section, translations, reflections, lines of reflections, and dilations, which are like stretching. So just a few functions to remind ourselves about. These are parent functions. Okay, parent functions means that it's the most basic of a certain kind of function that you can have, and all other functions that share a similar shape are transformed or changed based on this original function. So for example, if we talk about the constant function is y equals a number. F of x equals a can be any number. It's a horizontal line, so if it's a completely horizontal line, it's going to look like y equals a number, and we call that a constant function because the y value never changes. X can be anything, x is all real numbers, and the range is just one number. In this case, it would be 1. Then we have the identity function. The identity function is a line that goes through 0, 0. So the identity function will always go through 0, 0, and it will always have this equation, y equals x. The reason it's called the identity function is because if I plug in the 3, I get 3. If I plug in 4, I get 4. If I plug in 5, I get 5, and so on. So it goes through 0, 0, and it has a slope of positive 1. That's the identity function. All of the ordered pairs have the same x and y values. Then we have absolute value function, which we talked about in our last section. Absolute value functions make pointy v's. Y equals the absolute value of x is the parent function, meaning that's the most basic absolute value function you can have. And anything we add or subtract to it, either inside or outside the absolute value, is going to move it based on this original parent function. The domain here is the set of all real numbers, and the range is y is greater than or equal to 0. Lastly, we have the quadratic function. Quadratic functions always graph as parabolas. That's the name of the shape of the graph, but the function itself is called quadratic. The parent function of a quadratic function is y equals x squared. That's the most basic parabola you can have. It opens up, its vertex is at 0, 0. And it has what we call a normal width because we measure everything else being wider or narrower based on y equals x squared. The a value here is 1, so this is like y equals 1 times x squared. So that 1 is the most basic width basically that we can have. Here again, the domain is all real numbers, and the range is y is greater than or equal to 0. All right, when we talk about transformations of functions, okay, and this is something we'll practice a lot in our next class. But if my function has a number added to it, a number greater than 0 added to it inside the function, then it's going to move to the left, that number of units. If I have a number greater than 0 subtracted inside the function, it's going to move to the right. So that's a little bit opposite maybe of what you would think. If I have a number added outside of the function, it moves up, and a number subtracted outside of the function moves down. Okay, so this would be something like if I have f of x equals x squared plus 2. This 2 is not inside of the squared part. It's just added outside the function, so it would match this situation. It would move 2 units up. Whereas if I had f of x equals x plus 2 quantity squared, that looks like this first situation here. That plus 2 is inside my function. It's being squared. So that would move 2 units to the left. All right, reflections happen with negatives. If I multiply my whole function by -1, it's going to reflect over the x-axis. And if I plug negative x into my function, it will reflect over the y-axis. So for example, if I have f of x equals, let's see, 2x minus 3, if I multiply the whole thing by -1, so I'd have negative 2x plus 3, that would reflect over the x-axis. Whereas if I just plug in negative x and I get 2 times negative x, but it's still minus 3, so that would simplify to negative 2x minus 3, it would reflect over the y-axis. Lastly, we have dilations. Dilations are like stretches, either vertically or horizontally. So if I have a number multiplied by my function and the absolute value of that number is greater than 1, so we're talking like 2 or -2, 3 or -3, it stretches it vertically, so it's going to stretch it up and down. If the number that I multiply by my function is a fraction between 0 and 1, the absolute value is a fraction between 0 and 1, then it's going to compress, or sometimes we say it's going to shrink the graph vertically. It's going to like squish it down. If I multiply a number to my x value inside my function that's greater than 1, whose absolute value is greater than 1, it's going to give me a horizontal compress or shrink. It's going to squish it horizontally. And if the number inside that's multiplied by x inside my function is a fraction when I take the absolute value, it's going to stretch it horizontally. It's going to stretch it out from left to right. All right, so let's practice what this would look like. First, we're going to practice just identifying different kinds of functions. So this function here, we notice that it's a pointy v, so it has to be absolute value. This next function, you should recognize this shape as a parabola from Algebra 1. And if it's a parabola, it is a quadratic function. You should not just write parabola, you should write quadratic function. That is the function represented by the graph of a parabola. Okay, I want you guys to answer this one for me. Okay, hopefully you said B, constant function. Let's try another one. This one is an identity function. You can tell because it goes through 0, 0, and it has a slope of positive 1. Up 1 to the right 1, up 1 to the right 1, all the way along. Okay, so now we're going to talk about those translations or transformations that we were just talking about. Transformation is the general word. Translation is when I just move things left and right and up and down. So when we look at this plus 1 is inside of the squaring function. So what that means is it's going to give me a movement left 1 unit. So if you notice here, the blue graph is the parent function y equals x squared. So when I graph this function, y equals x plus 1 quantity squared, my vertex moves from 0, 0 to -1, 0. It moves to the left 1, but the width stays the same because I didn't multiply by anything in front of my function. Okay, try this one. Okay, this one is a translation, meaning it moves left or right. Since there's a -4 inside the absolute value, it's going to move to the right 4 units. If you go back and look at that chart from the beginning, you'll see that. So again, here's my parent function in blue. That's the parent absolute value function. My vertex moves 4 units to the right. So now my new vertex is at 4, 0 instead of 0, 0. All right, let's describe what's happening in this. Notice I have the absolute value, and out in front, it's multiplied by a -1. If you go back to the chart at the beginning of the video, that will tell you that it's going to be a reflection over the x-axis. So again, here in blue, they graph the original graph for you, the parent function, y equals the absolute value of x. And when I reflect it, it just literally flips over the x-axis. So instead of having the point 1, 1, we have the point 1, -1. Instead of having the point -1, 1, we have -1, -1, and so on. All right, try this one for me. Okay, hopefully you noticed that this would be a quadratic function, so it should graph as a parabola. This blue graph is the original parabola. That -1 in front multiplied by x squared means a reflection in the x-axis, so it just flips over the x-axis. Okay, here we're going to talk about dilation. So this is when we multiply by something that is different than -1. So in this case, I'm multiplying outside of my absolute value function by 1/2. When I multiply outside by a fraction whose absolute value is between 0 and 1, then it compresses it or shrinks it vertically. Okay, so this is what the new graph of that would look like. Here they didn't graph the parent function for you, but my parent function would have gone through these points here. So notice this would have been the point 1, 1, 1, 1. My new point is 1, 1/2. It only goes up half as high. This is the point 2, 2. My new point is 2, 1. So instead of going up 2 units, it was cut in half and only went up 1 unit. And it goes that way all along both sides of my absolute value graph. Try this one. Okay, so notice this time this is different than the last one because the 2 that I'm multiplying is inside my absolute value. According to the chart at the beginning, it's a dilation, and when I multiply inside by a 2, it's going to stretch my graph by 2. Okay, there's 2 ways to talk about this. Sorry, I'm pausing a little bit because I think they're saying something different than what they said. This can actually be described 2 ways. If you went back to the chart at the beginning, you might have said that it had a horizontal compression by 1/2, which you can also see is happening. So in this case, it looks like it was stretched vertically, which is true, but we could also have said that it was horizontally compressed. So my parent graph would have gone through 1, 1, 2, 2, 3, 3, and so on. But instead, this point goes through 1/2, 1. So my x, instead of going to 1, only went to 1/2, and then it went up 1. If I look at the point 2, 2, right, that's my parent function point, the corresponding point after my dilation is 1, 2. So my x value got cut in half. What happens though is that sometimes horizontal and vertical compressions or stretching can look the same. So when I compress something horizontally, it looks like a vertical stretch as well. Sorry if that was a little confusing. We can talk more about that one in class. But I would have accepted either one of these answers if it was a test or quiz or something like that. Okay, let's look at this word problem real quick. It says that the function f of x equals -1/2 times the quantity x minus 5 squared plus 12.5 can be used to represent a parabolic archway, so an arch that's shaped like a parabola. We want to describe the transformations, and you can see here we have a lot of transformations going on. There's 3 or 4 of them. Okay, so here in the blue, they're showing me the original function. When I look at the way this function is written, when I see that x squared here, the squared, I know that this is a quadratic function, meaning that it will look like a parabola. So when I look at the graph, like, okay, the -5 inside of my function moves it 5 units to the right. Remember, a negative number inside the function moves it to the right. So it's going to go to the right 5 units. This number that's added on the outside means it's going to move up or be translated up 12.5 units. It's right 5. And this -1/2, the negative means it's going to be reflected over the x-axis. And the 1/2 multiplied in front means it's going to have a vertical compression by 1/2. So let's look at the graph here and see if that's true. So notice my graph, my vertex moved from 0, 0. It moved to the right 5 units. Okay? Then it moved up 12.5 units. So the 5 that was inside, let me rewrite this here. So that 5 moved it to the right 5. This moved it up 12.5, so that's my new vertex. Then the negative flipped it over, and the 1/2 compressed it vertically. Okay, so it's compressed more than it would have been originally. That's a little hard to see from this graph, but we will look at that tomorrow.